Welcome to Math 2318. This is section 7.1. In question 1 here, we have matrix A. And looking at matrix A, we'd like to know, is it symmetric? Now there's a formal way, and then there's a common sense way, just looking at it because it's small enough. If you look at matrix A and don't focus on the diagonal because the diagonal can have different numbers. But if you look at the numbers off the diagonal opposite each other, they are the same. So it is symmetric. Now formally, here's matrix A, and now form A transpose. And when you form A transpose, you see that the matrices are exactly the same. So that's our definition of symmetric formally, is if A equals A transpose, then the matrix is symmetric. Alright, so let's see, what about matrix A here? So again, if you look at the diagonal, and if you look at the elements off the diagonal, are they the same? And here the answer is no. And you can see that formally if here's matrix A, here's A transpose, clearly they are not the same, and so matrix A is not symmetric. Alright, so we want to determine if this matrix is orthogonal. And if it is orthogonal, we'd like to find the inverse. Alright, so it's small enough we can actually physically do this. So let's see, here's matrix A. A inverse is 1 over the determinant of A. You switch A and D and then the negative of the others. So to form the determinant is pretty easy. Downward diagonal, which is 1/2. Minus a minus 1/2, so the determinant is just 1. And A inverse is, we can't really switch the diagonal elements, those are the same. It's the negative of this, negative of that, alright? And so I also form A transpose. And if you look, you see that A inverse is exactly the same as A transpose. So yes, it is orthogonal. In our next question, we'll see another way to go about doing this. So in question 4, I want to determine if A is orthogonal again. And in this case, it's a 3 by 3. So I'm not anxious to go try to find A inverse. Well, let's see. If A is orthogonal, then A inverse will be the same as A transpose. Now, A transpose is pretty easy to find. So if I can just calculate what is A times A transpose, and I look to see, is it the identity? Well, if it is, that means that A transpose is A inverse and A is orthogonal. So let's see. Here's A, easy to form A transpose. And so now multiply it together. So I would get a 4/9, a 1/9, and a 4/9. So 4/9, 1/9, another 4/9, 9/9, and I get the 1. Now you can check all these other elements, but what you'll see is you exactly get the identity. So A transpose is A inverse. I don't have to find anything. I know exactly what A inverse is. All right. In question 5, we want to orthogonally diagonalize the matrix. We want to find the orthogonal matrix P and the diagonal matrix D. So here's matrix A. First thing I need to do is find out what are the eigenvalues of this particular matrix. Alright, so we form this determinant, get my characteristic polynomial. I see that it factors into eigenvalues of 12 and 6. For the eigenvalue of 12, I now can find what is its eigenvector. Alright, so all that we did before. The only new thing is we're going to normalize it so that its length is exactly 1. So the magnitude of this vector is 1 squared plus 1 squared, or the square root of 2. So divide through by that so that this vector is normalized and has a length of exactly 1. Repeat the same process for the eigenvalue of 6. So I get minus 1, 1, and again I normalize it. Alright, so my diagonal matrix D is simply the eigenvalues. In matrix P, for the eigenvalue of 6, this is its eigenvector. For the eigenvalue of 12, this is its eigenvector. So not too difficult in the 2 by 2 case, but representative of what you would have to do for larger matrices. Alright, in question 6, we want to use matrices P and D to construct what is called the spectral decomposition of A. Well, what can we say here? Well, first, some things about the spectral theorem. First is the spectrum of A are the eigenvalues of matrix A. And it turns out that if all the eigenvalues are real numbers, and each has a multiplicity of 1, so the dimension of each eigenspace is exactly 1, and the eigenspaces are orthogonal. The spectral decomposition takes the eigenvalues, multiplies it by the eigenvectors in the combination of eigenvector 1 times its transpose, and then 2 and 3 in the same way. And that's why you see here that the spectral decomposition is 7. So my first eigenvalue multiplied by, here is u1, the eigenvector that goes with 7, eigenvalue of 1, u2 is the eigenvector that goes with that, and then finally the eigenvalue of minus 5 and its corresponding eigenvector u3. So to get these, you just take u1 times u1 transpose, and similarly all the way across the across here. And so what we get is called the spectral decomposition of A. You might be wondering why all this talk about eigenvalues and eigenvectors. One application is in differential equations when you're looking at systems. It turns out that if A is able to be written as a diagonal matrix, it's easy to do E raised to an exponent of A, which is a solution to some systems of differential equations.